Right, so let's have a look now at the start of the year 13 work on stationary points and points of inflection. And there's going to be a couple of subtle differences in this work. I'd like us to first start off by considering the curve y equals x to the 4. And what we're going to do is work through the logic of working out where the stationary points are for this particular curve, and then we'll identify their nature in the usual way that we did in year 12. And you'll see that we hit upon a little snag. So first of all, I'm going to work out dy by dx, and we're going to use the power method on this. 4 to the front, power goes down by 1. So dy by dx is 4x cubed. Now if I want to work out where the stationary points are, I put equals 0 because I know the gradient function is equal to 0 at stationary points. We now have a little equation to solve. So if I share this by 4, share that by 4, I get an equation to solve, and that's a cubic equation. So technically speaking, there should be 3 different answers. But in this particular case, if you think about it, if you cube root both sides, because that's the easy way to do it, there's only one unique answer. So there's only going to be one point here, which is a stationary point, and it's at x equals 0. To be able to work out what the y value to go with it is, just simply put 0 back into the equation that you're given, and you'll find that y is equal to 0 to the 4, which is 0. So we end up with a stationary point at the origin 0, 0. Okay, let's work out what the nature of this stationary point is. So if I now work out our year 12 technique for stationary point identification, we work out the second derivative. The second derivative is found by differentiating 4x cubed. Remember, the 4x cubed was the value of dy by dx, not the x cubed which we used here to solve the equation by sharing by 4. It's the 4x cubed which we use. 3 to the front, 12 x squared. There is d2y by dx squared. Now we say at x equals 0. The value of the second derivative, put 0 into there, you get 12 lots of 0 squared, which is equal to 0. And so if you were using the year 12 sort of logic as to identifying this stationary point, we would say that that's a point of inflection. However, in a previous video that I recorded, which I hope you've watched, I did say to you there is a little flaw in the logic of that. Because you should know from your year 11 work on sketching curves that y equals x to the 4, if I just make a little bit of space over here, y equals x to the 4 is just a U shape which sits on the x-axis like so, with the bottom of the U at 0, 0. That's what y equals x to the 4 looks like. It's a U shape. It's a similar U shape to y equals x squared, but because it's power 4, it's a bit steeper than the x squared graph. So that's what it looks like, and you can quite clearly see that 0, 0 is a stationary point, but it's not a point of inflection, which you might consider to be the case from that bit of calculation work there. So you can quite clearly see there's a flaw in the logic. d2y by dx squared equals 0 is a point of inflection. What we say instead is, if you work out the second derivative and it's equal to 0, that this is what we call an ambiguous case. Ambiguous. In other words, it could be a point of inflection. Indeed, it's the only situation that can arise where it is a point of inflection. If it's going to be a point of inflection, that must be 0, because if it's positive, it would be a local min. If it's negative, it would be a local max. So when we come out with an answer of 0 here, it could be a point of inflection, that is true, but it is also a situation whereby it could be a local minimum, as we've got here. So it's what we call an ambiguous situation. So you've got to be really careful when you're identifying what type of stationary point we've got. If you work out the second derivative equals 0, it might be a point of inflection is all you can say from now on. You cannot say for sure it is. And in the following video, I'll show you how we take a situation like this and we decide, is it a point of inflection, or is it indeed, as we've got here, a local max or a local min. And I don't want to make that into a really long-winded video, so I'm going to stop at that point and just show you the ambiguous nature of the second derivative being equal to naught. And in the following video, I'll show you how we get this to be a local minimum. Okay.